Hello everyone, how have you been? I hope you people have been doing well. I'm back once again. My name is Avinav Banerjee, and today I am back once again with this topic named as Four Legend Equations After 1 year. And let me recall you first that a previous lecture session was being uploaded in the year 2020 on the topic of nuclear physics. So today we are going to know about this four elegant. Elegant means that's a synonym of beautiful. Elegant equations. So these four set of equations were being given by the Scottish physicist whom you people might have observed with a long white beard named as James Clerk Maxwell. So we are going to deduce those four equations given by the great James Clerk Maxwell, and which unified electricity with magnetism. So I can say it over here that electricity got unified with magnetism, which was a dream of the great English physicist named Michael Faraday. So it was a dream. So it was a dream come true moment when at the University of Cambridge, James Clerk Maxwell formulates those four equations in one of the famous journals of physics named as, or the famous journals I have to mention by James Clerk Maxwell, which was named as a dynamical theory of electromagnetic field. So this was a journal on which James Clerk Maxwell published his four equations in the year 1865. He started working at the University of Cambridge. He was already working at the University of Cambridge. He started working in between this tenure, that is, was 1850s to 1870s. You can say in the mid 19th century. So finally, he discerned out the equations accordingly and finally published it in a single form in the year 1865 on the journal. A dynamical theory of electromagnetic field was the name of the topic, you can say, of the research article on a journal. So we are not going to discuss about the history that much, but perhaps I can give you a coins of, or you can say the chronological order of determining which sort of invention took place in the context of electrodynamics. So we'll be getting started with Coulomb's law, which formed out to be the basic building block of electrodynamics. It was coined in the year 1780 during the late 18th century, followed with the Ampere's law, which was formulated in the year 1825, followed with Faraday's law in the year 1834, and finally Maxwell's formulated equation in the year 1865, which I've already mentioned it over here. It was already mentioned it over here, the date. So we would be getting started. So this was nothing but the history and the actual situation, the actual moment. If I can mention you that it was an evening, or you can say it was about to be the time of dusk, when a young man, James Clerk Maxwell, as a young man with a goatee beard, he went to Michael Faraday. Michael Faraday was being shown as an old man. It's an obvious thing. He was quite senior to James Clerk Maxwell, and he just gave his theory. He just make him get a glimpse of those four set of equations, which I would be writing it down over here, which are as follows. Let's start with the first equation. Del dot D is equal to rho. Number 2, del dot B equals to 0. Number 3, del cross E is equals to minus del B by del T. And fourth, del cross H is equals to J plus del D by del T. So these are the four Elegant equations. These are actually our four Elegant equations which I was referring about, which paved out a historic moment in the field of science and technology. These four equations by which we are able to, I'm able to write down or scribble the equations at this point of time, and you are able to watch it right now. You can say all these equations are going to describe the essence, the property of electromagnetic waves, and we are able to watch, we are able to design this laptop, this mobile phone, or even the pen tab, which I am using it right down to scribble down the equations. Each and every one are going to harness electromagnetic energy. So that is why I would be saying that this four Legend equations change the face of the world. So this is what it's all about. So we'll start deducing the equations one after the other. So we'll start with the first equation. So before that, I was just trying to mention that after observing these four equations, one interesting fact which I was about to share it during the initiation of this lecture session itself, but somehow I thought about mentioning it at a specific interval of time when I would be quite exhilarated to mention about these four Elegant equations. So after observing this four equations, or you can say after the instant when James Clerk Maxwell made Michael Faraday get glimpse of these four equations, he gone through the proofs, and after that, which I would be doing it right now over here, he started crying. To be more specific, Michael Faraday was shed into tears, and he just embraced James Clerk Maxwell with his open arms, and that was quite an emotional scene which I would be thinking about and would be able to observe. And for a man of science, definitely that scene is going to make you understand the importance of someone's initiative work. So this is a message for all the scientists and the engineers I would be just trying to mention. Obviously, this lecture session is made for the graduate students, graduate engineering students who are pursuing their respective courses in the field of electronics and communication, or electronics or instrumentation, because this topic is of great importance for the engineering students and the physics students, the master's level physics students and the sophomore level physics students as well. So we'll start with the very first law, which is being mentioned as del dot D is equals to rho. So first of all, we'll start, we already know about vector calculus quite very well. This del is named to be as your nabla operator, is referred to be as, the name is nabla operator, and we are having, it's an operator which is used in vector calculus, which is having its equivalence, that is partial change with respect to one of the axis. Either you choose it to be as your x-axis, del by del xi cap, either you choose it to be as your ordinate or y-axis, making it to be as del by del y of j cap plus del by del z of k cap. So this is the exact interpretation of this del. So we are going to use this operator to determine and formulate this Maxwell's 4 elegant equations, or I can also write it down over here, that is Maxwell's 4 equations. So this is what I would likely to mention it over here. So let's get started. Somewhere like nabla operator, that is del by, so this is what I've already mentioned it. So how to do it? So we know, so have a look on the equation first of all. That means this, what this equation is trying to resemble, what this equation is trying to specify us. It is trying to specify that is divergence of electric field intensity is equal to the volume charge density. This is, in other words, if I want to say, I would be saying it like that. And this is nothing but a deduction of one of the most basic equations which we usually use to calculate the electric field in a much more simplified way. Yes, you are right, my friend, you are thinking, your way of thinking is absolutely correct. That is Gauss theorem or Gauss law, which states that del, so I would be writing down the exact equation over here, which states that closed integral of electric field around a surface, surface integral, or alongside of the surface I would be saying, or alongside of the surface contour, anything, any statement I can put it over here. Integral of E dot ds is equals to charge enclosed divided by epsilon naught. And we already know, if I just try to denote, like suppose we are having a continuous symmetric object. So suppose we are having certain n number of charges which are going to be present inside of it. So let us say we are having certain number of charges which are being present inside of it. So we can say, let us say we are having n number of charges, so we would be writing it down as nq or qn. So this n charges, n into q, would be the charge enclosed inside of this Gaussian surface, and the contribution of electric field would be due to the presence of all these charges. And it's an obvious thing, like this is the dot product of this electric field vector, and this is going to be referred to be as your area vector or the surface vector as well. So let us say we are having the electric field lines which are going to be in this direction, let it be, and in this direction, and the area vector, the ds vector, would be also, it's obviously, it's an obvious thing that it would be always perpendicular to the surface. So in other words, if I want to be much more specific, because sometimes people are going to get quite confused in this case, so I would be just trying to mention it accordingly. So this ds vector, let it be somewhere like that, it's going to make some angle the unit vector of this area vector is making some angle of, let us say, theta with respect to, let's try to write it down by some different color, that would be much more specific over here. It would making some angle of theta. So we can write down the dot product of them. We already know that the dot product of electric field and the area vector could be written as E dot ds, magnitude of electric field, into ds cos theta, where theta is the angle in between electric field and the area vector accordingly. So we already know the Gauss law very well. So we are just going to deduce this expression in a much more specified way. So if I just try to write it down somewhere like this, it would be somewhere we have to just try to write it down the expressions accordingly. Yeah, so we would be getting started accordingly. So we can write it down it to be as, once again I would be writing down the equation. And finally, I would be using, I can write down, I can just cross multiply this, it's going to become Q enclosed. So this is going to become this equation. As a result, epsilon naught E would be, the product of epsilon naught E is going to give us a value of the electric field intensity. So this is going to become D dot ds is equal to Q enclosed. So this charge enclosed, because we have to find out an equation based upon the property of the divergence. Divergence means flow of anything, just like a ideal fluid will try to flow. In a similar way, the charges will intend to flow. So in a similar way, I can write down this charge enclosed can be written as integration of the volume charge density with respect to infinitesimal change in the volume, so rho dV. So as a result, my equation becomes equal to my equation would be coming equals to, we can use, is going to be equals to rho dV. So now we can apply divergence theorem which states that any area integral can be transformed into a volume integral by the means of using a divergence operator before that as a prefix of that vector. So del dot A dV, this is what I can write it down. So this expression, this very expression, on the other hand, we can write it down as del dot D dV becomes equal to integral of rho dV. Now we are having the expressions on the left hand side and the expression on the right hand side, they are having the same differential variable. So I can remove the integration sign and the integrand. So as a result, my expression becomes del dot D is equal to rho, which pertains us the first Maxwell's equation. So this is what I can say it for the first equation. Now we'll start for the next equation, the second Maxwell's equation, which was being mentioned over here. Here it was being specified. The first one is being done, which is nothing but a modification of the Gauss's law. And the second one would be quite interesting to obtain it accordingly. So we can write it down. The second equation, how are we supposed to determine it? So for the second equation, we are going to use Biot-Savart's law. Everyone knows about Biot-Savart's law quite well, it seems. So the a current flowing in a certain volume. We have to consider a certain volume once again, and a current will try to flow. A current starts flowing, let us say somewhere like this. This is going to be the direction of the arrow, which I can write it down, which I can consider it in this case. And let us say these coordinates are going to be p x dash, p dash, let it be, and this point is going to lie outside that particular surface which I have taken under consideration. So it's going to be p x comma y comma z. So we can write down the volumetric representation of Barth-Savitz's law could be written as b as a function of r could be written as mu naught by 4 pi integration of, we have to consider obviously current is not a vector, we know that thing very well. So there must be a particular entity of current which could be treated to be as a vector. So we can choose the current density to be as one of the options. So j r dash, j dot r dash cross r vector, this is what I can write it down, and this is going to be unit vector actually, not a vector. So we can denote it by the means of a unit vector actually. So let it be. So whatever I have wrote it a few seconds back, let it be like that itself. So j r dash cross r vector. So this expression can be modified and written as mu naught by 4 pi j r dash vector cross, this r vector could be denoted in terms of magnitude and direction. We must be knowing that thing very well. So we can write this thing as, so this is nothing but, there has to be a slight change. I use the arrowhead as a superscript, but I have to use a cap because it's denoting the unit vector of r vector actually over here. So we can use it as our cap. So r dash cross, this could be written as r vector divided by modulus of r vector square. So this is what it's going to become, and over here it should be dv. So let us say the volume of this surface which is being bound, which is being depicted in pink, is having infinitesimal volume, its elementary volume is being mentioned as dv. So I would be writing it down over here as dv. So we just have to solve it, and we have to find it out. Like what we have to do is, we just have to use del dot b. We have to use the divergence of this expression. So this expression, as a result, I can write down. So we can, I would just try to skip 2 steps and will try to show you like how the expression would seem out to be like that, and why it's going to get formulated to be as 0. So I would be showing it down accordingly. So del dot b, so this expression becomes equals to, del dot b becomes equal to, we can write down mu naught by 4 pi is constant. So obviously it's going to be taken outside of the entire mathematical interpretation of vector calculus operation which we are about to use, which we are about to consider it over here in this case. Mu naught 4 pi del dot this expression j dot r cross r vector, it's going to be r cap actually, not r vector square. So this is how the expression would seem out to be like that. So we just have to solve for it, and we can use in between. So the technique, the trick which we can use it, that would be of your scalar triple product, which just tries to denote that what would be happening if I use del dot a cross b. So how are we supposed to write down the expression? So this expression we can write it down as b dot del cross a minus of a dot del cross b. So this is the entity, this is the identity of the entity which we can use it over here. So my expression becomes, we can write it down over here, that is del dot b equals to mu naught by 4 pi. So this expression is going to become r cap r square is going to come outside of the brackets, dot del cross jr dash minus of jr dash del cross. This is what I would be getting as an expression over there. So this term is negligible. This term I can just give a try to neglect it. Del cross jr, the curl of, we already know that the dot product or the divergence of the current density is going to give us infinitesimal change in the volume charge density, which is going to pertain us the equation of continuity. But in this case, if I am going to use del cross j dot r, which is not going to have any such significance, any such specifications over here, so the curl of current density doesn't exist, so I can easily write it down over here. That's going to become 0. Similarly, this term is also going to become 0 as well, and as an expression my del dot b becomes equal to 0, which proves the second equation of James Clerk Maxwell, which pertains the physical significance. We can write it down that magnetic dipoles, only magnetic dipoles can exist, only magnetic dipoles can exist, because magnetic monopoles do not exist. Magnetic monopoles don't exist. So now we would be like moving forward for the third law of Michael Faraday, which paved out to be a successful equation formulation, named to be as a Maxwell's third equation. So the second equation has been done. So we would move towards the third one, which is del cross E is equal to minus del B by del T. So once again, by Faraday's law or Lenz's law, let's try to apply Lenz's law directly by applying Lenz's law. And Faraday's law, I've already mentioned that Faraday gave this law in the year 1834, which really motivated James Clerk Maxwell. One thing I would just try to mention, that is Michael Faraday was a hero for James Clerk Maxwell. So now let me continue the topic. So Lenz's law, which states that the induced EMF always opposes the cause which has produced it, and the cause is obviously the rate of change of the magnetic flux with respect to time. So in other words, I can also write it down as minus d by dt of into magnetic field into the cross section area. We already know this expression quite very well. So now let's try to formulate this entire expression in terms of an integrand form, like having expressions inside of the integral. So what sort of values are we going to use? So this epsilon, or this is my induced EMF. We already know that the negative gradient of this induced EMF is equals to electric field. We already know this expression quite well. So we are going to use this analogy over here. So my expression becomes, so my expression would be coming quite very well, very simply. So I will just try to reduce the expression over here itself once and for all, such that you people are not going to develop any such sort of sophistications while deducing it on your own. So we know that we will try to write it down directly. That is integral E dot dl. This is what I can, linear integral of electric field, which is equivalent to the electric potential or the induced EMF in this particular aspect, is equals to minus d by dt integral of b dot ds. Now we have to perform a transformation. Now there itself we have to use the Stokes theorem, needs to be used. Last time, if you can recall, while deducing the first Maxwell's equation, I had mentioned you regarding the divergence theorem was already being mentioned it over here. and subsequently I did mention it to you over here in this case. Have a look, just try to make you recall out of that. So over here we have to use Stokes theorem. Once again it tries to state that if I want to convert a linear integral in the form of a surface integral having in the form of a dot dl needs to be converted into ds in terms of a differential of the area vector, it's going to become del cross, which is also going to be referred to as curl dot ts vector. This is what I have to use it over here in this aspect. So my equation becomes, so this equation applying it over here, it's going to become epsilon, so we can write it down as directly del cross E dot ds. Have a look, we have already changed it, we have already transformed it into differential area vector is equals to minus d by dt integral of b dot ds. So once again we can just try to equate these two integrands having the same differential variable. I'm talking about the respect variable with respect to variable is the same ds ds. So we can just cancel the integrand term, we can just ignore the integrand term, and finally we can write it down that del cross E is equals to minus of dB by dt. So this is what we can say, this is going to be referred to be as your Maxwell's third equation. So let's come to the final equation. After that would be like ending up the culmination over here. Once I do, we are going to end up this particular set of equations. As a result, the third equation also got successfully proven. So we'll go to the last one, which is the most important equation, and we are going to use the concept of Ampere's circuital law. From there itself it's going to be deduced. Once again, it is a much more better technique, it's a much more useful technique as comparative to this rule, this law, to find out the magnetic field of any such object. But yes, once again it's having its own limitations, and even a high school student knows that thing quite very well, that Ampere's circuital law can only be applied for certain symmetric objects. So once again, without just going up to the deep investigation of Ampere's circuital law, we were just trying to write down the expression which pertains, that is closed linear integral of magnetic field is equals to permeability of the free space times the current enclosed. This is what I can mention it, this is what I can write it down over here. So now once again you have to use Stokes law, Stokes theorem. Once again it needs to be used because we have to convert linear integral into the formulation of surface integral actually. So let's try to write why we need to convert, why do we need to convert this thing, this expression of b dot dl into differential area vector form. The reason is quite simple, because this could be furthermore deduced as b dot dl is equals to mu naught multiplied by current enclosed. So this is, we know that current could be written as j dot ds, that means current density multiplied by the differential operator, differential of surface vector or differential of area vector, whatsoever you are going to name it. So b dot dl, so as a result I can write it down, that's now we need to change it. So now have a look, so this can be cross multiplied, so b by mu naught, this is going to become b by mu naught. So we know that b by mu naught is equals to the magnetic field intensity denoted as h vector. So h dot dl could be written as integration of j dot ds. Now we have to solve this expression. Now you can easily apply Stokes theorem from here to here and just try to make the magnetic field intensity expression in terms of curl. So I can write it down it to be as, so we can just try to denote it over here itself all the way. This is going to become del cross h ds, once again we are going to eliminate the integrand, integration sign symbol, and the variable, differential variable, they are proving out to be the same. So once again we can ignore it. So as a result we are getting del cross H is equal to J. So but the equation over here, if you are able to see, it's quite different. It's quite different. We are having some extra terms in terms of differential partial derivative of electric field intensity represented by this D symbol, if you are able to see it over here. So what are we supposed to do in this particular aspect? So once again we have to ponder upon the situation. So this is applicable for steady fields, steady magnetic field, and for time varying magnetic fields it's not. Now this is going to get violated in violation, I will write it down, in time varying magnetic fields. With time, so we have to use the concept of all sort of possibilities of the current density. What sort of current densities we can expect in time varying magnetic fields. So we will start from the scratch once again. So let's just try to initiate from the scratch, like how are we supposed to write it down. So we will start from the basics once again. So we will start with, now the expression was quite simple. We know that del cross H is equals to J. It's quite simple. Now for time varying magnetic fields, this J would be a collective sum of, this current density would be a summation of the current density due to the free charges plus the current density due to bound charges plus J due to certain modifications. So the modifications means, I would be just trying to mention, now the concept of drift current won't be holding for this J modification. So there itself the concept of diffusion current will come into existence, also known in semiconductors, it's being referred to as diffusion current actually, but in the context of electromagnetism, it would be referred to be as your displacement current. So now we have to just try to formulate the expressions accordingly. For free charges it's going to remain as it is. For bound charges there would be, we have to use the concept of intensity of magnetization. We have to write it down, that is del cross I is equals to, this expression is going to become as del P by del T plus J of bound charges. So you have to use this expression over there. So this J bound charges could be written as del cross I minus of del P by del T. So this I stands for the intensity of magnetization, which is equals to the dipole moment per unit volume, and on the other hand we are having this symbol of P, which is nothing but the polarization vector. So this is my polarization vector, and we know that it's equal to, it's having a mathematical interpretation equivalent to the electric susceptibility times the electric field. So we are going to use these expressions over here, and for modification we just have to use the concept, that is it's equal to rate of change of displacement current with respect to time. So as a result, if I know what we are going to use it actually, now that would be quite an interesting phenomena which we can just try to, we can just think about it. So that would be quite interesting phenomena, and you people are really going to enjoy, and all my ex-students and my previous students and my current students, all students are going to enjoy, even whether they are situated in India or outside India. It's for everyone actually. So now let's try to make the situation much more easier. So what are we going to do? Let's try to use it. So we have to do this Ampere's law, which we are having a del cross H is equal to mu naught into J total. We have to write it down. So this expression is going to be written as del cross H becomes equals to mu naught J free, referred to be as J subscript F, plus J bound charges, which I would be writing it down as J subscript B, plus J subscript M, which is denotes the modified current density expression. So now if I use the divergence, we have to find out divergence of curl. Actually we have to do it. We have to find out the divergence of curl. Divergence of curl. We already know the divergence of curl is 0, by the way. So which is nothing but what we are going to do right now. That's going to be quite interesting actually to observe it right now over here. Del dot del cross H is going to be equals to del dot the entire expression. Okay, fine. So this expression won't be existing actually. The mu naught term I have just overwritten it, because we have already use the ratio, that is B by mu naught is equal to H. So let's try to denote the expression accordingly. So del dot Jf plus this expression Jb can be written as del cross I minus of del P by del T. So let's try to write it down. Del cross I minus of delta P by delta T plus del D by del T. So this is what I would be getting. So now have a look right now. So del cross H, del cross I. So we can use the property of vector in this case. So this expression would be becoming equals to, we can write it down, that is this entire term becomes 0. So I can write down the expression becomes equal to 0 is equals to Jf plus okay, so this is going to be B by mu naught minus of I, which is equivalent to H minus of okay plus del by del T P plus D, where P is the polarization vector and D stands for the electric field intensity, which could be written as epsilon naught T. So there itself comes the concept of this expression. So as a result, the entire expression del cross H could be written as, finally I can write down del cross H would be equals to, this J free charges would be existing. So J free charges plus this entire displacement current, P plus epsilon naught denotes the expression for the displacement current. So Jf plus del by del T into epsilon naught T. So this is what I would be getting as the fourth equations. All the four Maxwell's equations have been successfully proven, and hopefully you have liked and enjoyed this particular lecture session up to the most. So we'll be back once again, maybe tomorrow, day after tomorrow, with a new lecture session on a new interesting topic on science, technology, even for Indian Physics Olympiad, International Physics Olympiad, for GATE syllabus as well. So also science and technology means engineering and science. Engineering and natural sciences are going to be discussed over here in my YouTube channel named as Physiker, which is a German word named to be as a physicist. A physicist should be pondering upon each and every situations, every realistic situations, while applying their exposition in all fields of interest existing on this realm, on this world to be more specific. So they should be science, technology, they are not discrepant with respect to each one of them. Technology is nothing but an application of mathematics, and that's what a physiker, a physicist is really capable of doing, and they are really going to enjoy while doing all the sort of things. So we'll be departing right now. It's Avinav Banerjee for each and every one of you. A very thank you very much. Maxwell's equation henceforth proven.